This video passes on orbital diagrams. Orbital diagrams are a step further than electron configuration. So you must have the electron configuration first, and then you do the orbital diagrams. These orbital diagrams will pull in those other two, or the last two, quantum numbers of the four. So electron configuration only deals with the energy level and the sublevel. Orbital diagrams pulls in the orbital orientation and the spin on those electrons. So orbital diagrams show how the electrons are distributed among the orbital orientations. Each orbital is going to be represented, or each orbital orientation is what I mean there, is represented by a set of parentheses. And electrons are shown by up or down arrows depending on the spin. So clockwise for one, counterclockwise for the other. The electrons in each orbital must have opposed spins. And we talked about it the other day. There will be 2 electrons in every orbital orientation. That's why the number of orbital orientations is half the number of electrons that each sublevel can hold. And that's in a chart that we filled in yesterday. So, if one arrow is up, the other one must be down. The first electron in an orbital is arbitrarily represented by an up arrow. Arbitrarily means that there's no real reason why. We just wanted them all to look the same and have an organized way to go about it. So we just said, hey, let's let the first one be an up arrow always. And everybody else said, okay. So that's what we do. First, let's talk about boron. With boron, it has an electron configuration, and that's always where you start with orbital diagrams, of 1s2, 2s2, and 2p1. So what we're going to do with our orbital diagrams is we're going to draw parentheses underneath these. And we'll draw one set of parentheses for each one as we go. And okay, so what we will do is S sublevel has how many orbital orientations? Remember, S is a sphere shape, and there's only one way to orient a sphere. So there's only one orbital orientation for an S sublevel. So we only draw one set of parentheses. Here we have another S sublevel. It is also only one way to orient that in three-dimensional space, so only one set of parentheses. If you will remember that P can hold up to 6 electrons, and it has 3 different orbital orientations. That dumbbell shape could be along the x-axis, along the y-axis, or along the z-axis. So I draw 3 sets of parentheses there. Now we have to go back and put our electrons in. So this is the number of electrons that we have, and there are 2. The first one's always up, and so the second one has to be an opposed spin, so it is down. If they don't have opposed spins, then they violate the Pauli exclusion principle and have the same set of 4 quantum numbers. So we're now to this one. We have 2 electrons, so first one's up, second one's down. Here I only have 1 electron, so I'm just going to put 1 up arrow right there and leave the rest of them blank. And that is the orbital diagram for boron. So it is going to include both the electron configuration and the parentheses with the arrows down there. Now, this little pattern holds pretty well, except for the P sublevel. We found that carbon, which just has 1 more electron than boron, has a most stable arrangement when the 2 electrons are in different orbitals with parallel spins. So if we look at carbon, its electron configuration is 1s2, 2s2, 2p2. So we'll draw parentheses. S only has 1 orbital orientation. This S only has 1 orbital orientation. P has 3 different orbital orientations. And again, the numbers of orbital orientations are located on a chart that we talked about before, or or wrote down before. So now let's map our electrons. We've got 2 electrons here, so first one's up, second one's down. Now we're to this one. First electron's up, second one's spinning the other direction. Now we're to these electrons. Here's where it gets just a little weird, but in a regular sort of way. The first electron goes here. The second one is not a down arrow in the same orbital. It is an up arrow, so it has the same spin as the other one, in the next orbital. Why? Because it's more stable, and atoms do things that are more stable. So that becomes the electron configuration for carbon. If I was working with it, and instead of carbon I was working with oxygen, then this number right here would be 2p4. So my first electron would go here, my second electron would go here, my third electron would go here, and then the fourth electron would be a down arrow right here. So what happens is in P, D, and F sublevels, they're going to, all the orbitals are going to half fill before any of them fill completely. And that leads us to our rule for today. It's just Hund's rule. In P, D, and F sublevels, each orbital half fills before any orbital completely fills. Now, I always want you to observe Hund's rule. How about you try iron and write its orbital diagram, pause this video cast, and then I'll put the answer here in just a second. All right, for iron, its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. So now I'm going to go in and put my orbital orientations. S has 1. This S has 1. P has 3. Now notice how I'm leaving spaces and everything's all nice and neat and organized. Don't cram them all there together because then I may not count right on purpose. All right, P has 3 orbital orientations. S has 1. D has 5. Didn't leave myself enough room, so we'll just put the others down here. Okay. Now let's go in and put our electrons. So back at 1s2, that means I have 2 electrons, so the first one's up, second one's down. 2s2, 1 electron's up, other electron's down. Now I have 2p6, so first one's up, second one's up, and the third one's up, because of Hund's rule. Then down, down, down. Now at 3s2, first one's up, second one's down. 3p6, first one's up, second one's up, third one's up, and then 3 down arrows, because of Hund's rule. 4s2, 1 up, 1 down, and then we get to 3d6, it is going to be 5 up arrows in a row, and then 1 down arrow in this first one to give me 6 electrons. The number of arrows must match the number that you have right there in all of them. All right, that's it for orbital diagrams.